Right, here is a video that's going to cover the entire magnetism and the motor effect unit. If you're studying at Edexcel, it's called SP12, but basically this is good for any exam board because the content for magnetism and the motor effect is very, very similar for everything. Now, when I'm covering it here, I'm going to be covering all the statements bit by bit. And we've got some more hidden over here as well. So I'll try to get through this video as quick as I can to cover all of these bits and pieces without making you feel too sick by spinning around all the time. Haha! Tell us what you think of this new style of video. Put some comments below whether you like it or whether I'm moving around too much. It's just making you feel sick. So first things first, let's get on to this first statement here. Right, 12.1. And by the way, this video covers triple, higher, combined higher, foundation, everything. If there's a particular statement that's triple only, then I'll tell you. And if there's a particular statement that's higher only, I'll tell you. So 12.1, recall that unlike magnetic poles attract and like magnetic poles repel. So what they're basically saying is if you've got a couple of magnets, north and south, and another magnet, north and south, these are going to repel away from each other. And likewise, if you had a couple of magnets here and you had two south poles next to each other, they would also repel, which is just a posh word for saying they'll move away. And opposites attract. So if you had a north next to a south, then they would attract together. It's a nice easy statement to start off with. Now here's an exam tip. Don't just say that these would repel, say that they will repel for one mark and they will move away from each other for another mark. And for these ones here, don't just say they'd attract, say they will attract and they will move toward each other. I mean, it's pretty obvious, but the examiners do like it to state that. Right, let's pop over to the second statement. (12.2) Describe the uses of permanent and temporary magnetic materials, including cobalt, steel, iron and nickel. Right, well, for starters, you have to know that they are the four magnetic materials that the examiner will want you to know. Now, if something is a permanent magnet, it'll be hard, such as steel. Iron is softer than steel, and that's the way I think about it. Because it's soft, it's just temporary. Which means you can easily magnetize it and then demagnetize it, which makes it perfect for being an electromagnet. You couldn't make steel an electromagnet. Well, you could, but it would stay magnetized after you turn the current off. Now the uses for one mark in an exam: permanent magnet, fridge door. When you shut your fridge, there's a magnetic seal to keep it shut. Temporary, your doorbells, electromagnetic cranes, speakers that you get your sound out of, listening to music, and microphones. Remember, I'm just going over the entire unit quickly, so I'm not going into too much detail in each of these things. But I do have videos for some of these things on my channel already. 12.3. Explain the difference between permanent and induced magnets. So a permanent magnet produces its own magnetic field permanently, like this. Now remember, the magnetic field comes out of the north and goes into the south. Out of the north, into the south. And it's like a butterfly shape. The examiner will often ask you to look at the magnetic field of the magnet. Now a permanent magnet has that permanent field around it. An induced magnet, well, induced just means created, or you've caused it to happen. If you take a piece of iron, which is a magnetic material, and you place it into the magnetic field, then that magnetic material will become magnetized. Now it'll get its own poles, so because that's south, this end will become a north. That'll get induced as a north, and that'll be a south there. And it'll end up with its own little magnetic field. Now this is the thing. If you then put another magnetic material, like a paper clip which is made of iron, and you make that paper clip touch this magnet, then the paper clip will become a little magnet as well. A little north there and a little south there, and then it'll end up with its own little magnetic field, and then you can put another paper clip touching that paper clip, and then that'll also become an induced magnet. And what the examiner will sometimes ask you is to prove that you can induce a magnet, and all you say is, check that this piece of metal first of all can't pick the paper clips up, then touch this piece of metal here with a proper magnet, and then that will induce magnetism into this piece of iron. And now I should be able to use this piece of iron to actually pick up these paper clips, which would prove that I've induced magnetism. Now, to show that it's only temporary, you would then take that magnet away, and then because this piece of iron is no longer next to the magnet, it's no longer in this magnet's magnetic field, this would not be a magnet anymore, and the paper clips would just drop off. .4 Describe the shape and direction of the magnetic field around bar magnets and for a uniform field, and relate the strength of the field to the concentration of the lines. So for a bar magnet, the magnetic field comes out of the north and then goes into the south, as I've just drawn before. Now where the lines are the most concentrated, that is where the magnetic field is the strongest. You'll notice that these lines here have got quite a bit of space between them. So what that means is that the magnetic field is not the strongest there. Now you can tell when a field is uniform. If that was all a big north magnet up the top, that was a big south down the bottom. Uniform is when the lines are equidistant apart, which means the same distance apart. Now the examiners like you to draw at least 3 lines. It may be better to draw, 4 or 5 just to get the point across. So this is a uniform field, which means the strength is the same everywhere, and that's because the distance of the field lines are the same distance apart everywhere. And make sure you draw your arrows to show that the field is going from the north to the south. If they wanted you to draw another uniform field that was stronger than this one, then it would look like this. Basically, the lines would be the same distance apart. I've just drew the north and the south magnets together closer, just because I'd run out of space, that's all. 12.5 Describe the use of plotting compasses to show the shape and direction of the field of a magnet and the Earth's magnetic field. Right, what you do is if you'd place a bar magnet in the middle of your page, and what you want to do is if you place plotting compasses at various strategic places, you'll be able to see which way the plotting compass points, and the plotting compass will show you the shape and direction of the bar magnet. So this plotting compass would point that way. Remember, the magnetic fields are coming out that way, so that would go that way. That little compass would point there. Now remember, the field comes out and comes round, so this compass would point that way, and then it would come this way, and then the magnetic field's coming there. Now, remember, the magnetic field goes into the south, so these compasses would point that way like that. This magnetic field would come out of here. It would be travelling this way. So this is the direction that the compasses would be pointing. And then all you do is you would then join them up. Now the beauty of using compasses is not only does it show you the shape, but it also shows you the direction. You can get the shape by using iron filings, but iron filings won't tell you the direction. So this shows you the shape and the direction. And obviously the more you do it, the more lines you'd end up getting. Now you can just use one plotting compass. Just put the compass there, draw the arrow, move the compass there, draw the arrow, move the compass there, draw the arrow. So you don't need all of these plotting compasses. You could just use one, and that's what you could tell the examiner in your exam. Now we also use plotting compasses to get the Earth's magnetic field. Now the Earth basically behaves as if it's got a magnet inside it. Now the strange thing is that the geographic North Pole is actually the magnetic South Pole. And the geographic South Pole is actually the magnetic North Pole. Now remember, that makes sense, because if you've got a compass, the compass will follow the field lines and it'll point to the geographic North Pole, right? Remember, the field goes into the south, comes out to the north, goes into the south, like that. Now you'd get exactly the same shape around the Earth as the shape around a bar magnet. And what a compass is it's actually a little bar magnet with a little north and a little south. And remember, opposites attract, so that north is getting attracted to the south. That puts off a lot of people. But just remember, so the geographic pole is the opposite to the magnetic pole. If you don't believe us, you can look that up in a textbook, but I guarantee you it's right. So a compass always points north. But what that means is it always points to geographic north. And that proves that the Earth has got a magnetic field. (12.6) Explain how the behaviour of a magnetic compass is related to evidence that the core of the Earth must be magnetic. Right, well, I've just shown you that over on this previous part here, so I'm not going to go into that again. Alright, but that's your proof there. It's like going on a physics merry-go-round, this. Hey, dear me. We're all going to have motion sickness by the time this is finished. There's the dog outside wondering what I'm laughing at. And here that tail. A magnetic compass points north, proving the Earth has a magnetic field. That could actually be worth 3 marks. It's very easy to get them marks there. So I thought I'll write that down for you. 12.7. Describe how to show that a current can create a magnetic effect around a long straight conductor, describing the shape of the magnetic field produced and relating the direction of the magnetic field to the direction of the current. Basically, all that waffle is saying, use the right hand grip rule. Right, so if you've got a big long wire, so that is the long straight conductor, and if you pass a current through it, let's say the current's going upwards. If you take your thumb, your right hand, and point your thumb upwards, and then if you grip your fingers round like that, there's your fingernail, look at this. I mean, pork sausages here. I don't know what. Anyway, right. There you go, a bunch of bananas. Right. Your thumb shows which way the current's going. And your fingers would show you the direction of the magnetic field. So this is the right hand grip rule. Now the best thing to do here is you'd have a piece of paper, and that wire is coming through the middle of the piece of paper, and if you put a compass or compasses on the top, one at the back, one at the side, one at the front, one over here, and what would happen is when you turn that current on, initially all the compasses would have been pointing north to line up with the Earth's magnetic field, but because you've turned the current on through the wire, the magnetic field of this wire is stronger than the Earth's magnetic field, so those little compasses will end up lining up with the magnetic field around the wire rather than the magnetic field of the Earth. And if you use the right hand grip rule, you'll notice that the compasses will start pointing that way, that way, that way, and then that way. So that's basically anti-clockwise. If you're looking down from the top, that field will be going anti-clockwise. So describe how to show that a current can create a magnetic effect around a long straight conductor, describing the shape of the magnetic field produced and relating the direction of the magnetic field to the direction of the current. Right, what that means is if you were to reverse that current, so if I draw it over here, if the current was now to go downwards, the magnetic field would reverse and it would now be going clockwise. Again, if you're looking down, bird's eye view, the compasses would now be going in a clockwise manner. Now there is another question as well that'll say, tell us about the strength of the wire. Well, basically, when you're next to the wire, you'll end up having a strong magnetic field. So the field lines would be close together. And then as you get further and further away from the wire, the magnetic field would get weaker and weaker. Once again, as represented by the distance from one field line to another field line. And also the magnetic field would be stronger if you had a bigger current. So the magnetic field is strong when you're close to the wire and if you use a bigger current. 2 marks in an exam. You're welcome. 12.8. Recall that the strength of a magnetic field depends on the size of the current and the distance from the long straight conductor. Right, well that's exactly what I've just said for 12.7. I've just been marking some exam papers, and that was a question that was worth 2 marks. Right, so that's the first 8 statements anyway. And what we've got is some more statements to follow. Sure, I could make a nice mind map once I learn how to get the best out of this. So you can see there's a few statements that are coming up now that are higher only. And this one here is triple higher only. Right, let's start with this over here. If I can find where it's gone. 12.9. Explain how inside a solenoid, which is an example of an electromagnet, the fields from individual coils add together to form a very strong, almost uniform magnetic field along the centre of the solenoid and cancel to give a weaker field outside the solenoid. Well, first things first, what's a solenoid? Right, it's basically a coil of wire. Now remember, if you put a current into a coil of wire, you'll get a magnetic field around the wire. Now I'll not go into all the ins and outs too detailed, But basically, a solenoid, you get the same shape magnetic field as you would if you were using a bar magnet. Now imagine that the current is coming in here. So it's going round the back, and then it's coming round the front. Then it's going round the back, and then it's coming round the front like that. So the current is looping round and round like that. Now what you can do is you can use the right hand grip rule, but this time your fingers show you the direction of the current. So if you had your right hand grip like that, and your fingers would sort of, this is a terrible picture here, your fingers would be curling like that. Now this time your thumb shows you where magnetic north is. So your thumb points which way the magnetic field is travelling. And remember, the magnetic field comes out of the north and goes into the south. So the magnetic field would come along this way. I should do a different colour really. Right, I'll do the magnetic field in orange. So the magnetic field would come along here like that, and as it got to the end it would curl around and come back again. So it's going into the south end and it's coming out of the north. Now I'm trying to draw this as accurate as I can. So things to notice is that here in the middle the field lines are uniform and they are very close together, which means the magnetic field is strong. So the fields from these individual coils are adding together and it forms a very strong, almost uniform. It's not quite uniform because as it comes around the corner here it's not fully straight lines, but in the middle it's almost straight lines. So a very strong, almost uniform magnetic field along the center of the solenoid. So remember, a solenoid is just a coil of wire. And what happens is in this area here and this area here, you get magnetic fields cancelling out. Now, I don't want to go into too much detail and start confusing you, but you end up getting a magnetic field around this bit of the coil here and a magnetic field around that bit of the coil, and they cancel out along that region and that region. You'll have to watch a video once I eventually make it to explain that a little bit more. So the field is not as strong outside the coil and it is very strong inside the coil. Okay, and that part about the cancelling, that's these regions here. I'll be honest, as long as you say it's strong in the middle and it's uniform and you've got straight lines like that, and then around the outside just do your lines a little bit further apart from each other and just say that the magnetic field's a bit weaker on the outside than it is on the inside. And that's all you need to know. That's all the examiners will be bothered about. Statement 10. Higher only. Recall that a current carrying conductor placed near a magnet experiences a force and that an equal and opposite force acts on the magnet. So what that basically means is if you've got a horseshoe magnet, well, any magnet really, but I like to do this with a horseshoe magnet. We'll say that's the north end of the magnet, that's the south end of the magnet. Well, that magnetic field would be going from the north into the south like that. Now, if you come along and you put a wire going right through that, especially at 90 degrees, if you put a current coming out of the paper, you'll get a magnetic field around this wire. Now, if we use the right hand grip rule, if you were to point your thumb out of the screen towards you and look at your fingers, which show you the magnetic field, Remember, this is the right hand grip rule as applied to a long thin conductor, not a coil of wire. So the right hand grip rule has got two uses, one for a solenoid and one for a normal wire. So we're just doing it for a normal wire. So your thumb would come out like that, and your sort of fingers are going round like this. So your thumb shows you the current this time, not the field. And your fingers show you the field. So the magnetic field would be going around the wire like that. Now, the magnetic field of the wire is going to affect the magnetic field of the permanent magnet. And what you end up getting, if I do it in red, the magnetic field would get pushed downward like that. Now, what's going to happen is the wire will experience a force upwards, and the magnet would experience a force downwards. And as it says here, the force will be equal in size, but they'll be opposite in direction. Now all that you will see is the wire moving upwards, because the wire is only light. The magnet is much heavier, and besides, it's probably resting on a desk. You won't see the magnet moving down. You'll just see the wire moving upwards. And there you go. Equal in size, opposite in direction. Sorry, I've just came off the screen there. Just move that along there like that. Look at that. Oh, that's the beauty. That's the beauty of the 3D software. Look at this. Oh, close up. Hey! Alright. So there you go. Very nice. 2 marks in an exam. Easy peasy. Okay, here's another statement. Higher only. 12.11. Explain that the magnetic forces are due to interactions between magnetic fields. Right, well, I'm not going to draw that again because that's exactly what I've just drawn there. All right. Magnetic forces. So that's one of the forces going upwards and another force going down. They are due to interactions between the magnetic fields. Now what I could do is I could slip the word magnetic in there. The magnetic forces are equal in size and opposite in direction. There we go. 12.11, easy peasy. Right, another higher only statement. We're coming up close to the end now. So if you're still with us, well done. Remember to subscribe to my channel, as it helps us reach a larger audience to help more people. 12.12. Recall and use Fleming's left-hand rule to represent the relative directions of the force, the current, and the magnetic field for cases where they are mutually perpendicular. Perpendicular means at right angles. So what you'll have the movement of the wire due to a magnetic force would go upwards. And what you'll have is the magnetic field coming out at right angles like that. And then you can also factor in the current. So this would be the current coming out of the screen. And that would also be at 90 degrees. So the current and the magnetic field are at 90 degrees. And also you'll have the magnetic field and the current would also be at 90 degrees. So they are mutually perpendicular. Everything is perpendicular, so 90 degrees to everything else. And what you'll do with Fleming's left hand is you represent those directions with your thumb, your first finger, and your second finger. And then obviously there's your 2 little fingers that's left over there. Now the way I like to think about it, I've just drew the nail on there. The thumb represents the movement of the wire. Now that is caused by the magnetic force. Some people like to say thumb is the force. I don't like saying that. And that's because I prefer using an F for the first finger. Shows you the field. Oops, I should have done a big M there. Thumb for the movement. First finger for the field. And this is the second finger. I'll do it in a different colour. The second finger shows you the current. Second finger, current. Okay. So if I just quickly draw a little example for you. So there's our horseshoe magnet. You'd line your first finger up, pointing from left to right across the screen. Now actually, knuckles is north, fingertips is the south. North, south, knuckles, tips. Right, I like that. I made that up years ago. Or I first came across it years ago. I can't quite remember if I was the bloke who made it up. It sounds like me. Knuckles. Fingertip. South. Now if you've got a wire, and the wire's coming through this way, and we'll say the current is coming that way. So you get your second finger and point it out the screen at you, at yourself. And what that'll do is that'll leave your thumb pointing upwards. So this wire, badink, is going to have a magnetic force upwards, so the movement would be upwards. What the examiner will say is if you were to turn the current on and that long thin conductor was in the magnetic field, what will happen to the wire? And you just use Fleming's left-hand rule. It's Fleming's left-hand motor rule, by the way, because the motor creates the movement, you know, in a car. And by the way, in England, we're motor on the left. So that's how I remember Fleming's left-hand rule is the motor rule. Now, if we were to reverse that, the wire would go down, right? If you were to, I'll quickly draw it. If you reverse the magnetic field, so now it's north on that side and south on that side, and we'll do the wire still coming out, only change one thing at a time. The current still coming out the screen. Now, so you point your second finger coming out towards you, but this time you have to reverse your first finger because the field's going from right to left. Now don't snap your wrist when you do this. Now your thumb will end up pointing downwards. So now the movement is down. And what the examiner might ask you is if you reverse the magnetic field, what would happen to the wire? And you say, well, the wire would move downwards this time rather than upwards. And the same thing would happen if I go back to this first scenario, but instead of the current coming outwards, if the current went inwards. Now I have got a nice little video on this. So back to the north there, back to the south there. So the magnetic field always goes from north to south that way. So point your first finger, shows the field, point it to the left or right. And this time though, the current's going into the screen. So point your second finger for the current away from you. And then what you'll find is that your thumb is pointing downwards. So compared to this first scenario, right, with the current coming outwards, the wire went up. Now with the current coming inwards, the wire goes down. And the keys to the kingdom are, you just tell the examiner, if you reverse the magnetic field, it reverses the movement, as I've showed you between these two, or if you reverse the current and keep the magnetic field the same, that also reverses the movement. So just remember the word reverse. Right? If you reverse one thing, it reverses another. Two more statements and then we're done. Statement 13. Higher only. Use the equation F equals B times by I times by L. So what that basically means is that the force on a conductor at right angles to a magnetic field carrying a current in newtons, so the magnetic force, and that equals the magnetic flux density measured in Teslas or Newton per ampere meter multiplied by the current in amps multiplied by the length of the conductor. That's carrying the current in meters. So do you know all those pictures that I've just been showing you? They'll just say something like, there's the wire. They'll tell you the size of the current going down through the wire. They'll tell you the strength of the magnetic field around the wire, which is the magnetic flux density. And they'll also tell you the length of the wire. And you basically just multiply those three things together in order to get the force that's acting on the wire. And that force would be acting upwards or downwards. So it's not as difficult as it seems. Now, just in case you can't rearrange the equation, let's make sure you're happy with this. So if you've got F equals B times by I times by L, do a magic triangle, do a top shelf, split the bottom bit up into 3 bits by doing 2 multiplied signs. Now I've got room for something times by something times by something, so shove them in, something, so it's B times by I times by L, and then put the F on the top, and then you cover up what you're looking for. So if you're looking for B, B would equal, cover up B, and you're left with F over I times by L. So you'll get marks for being able to rearrange the equation. What if I'm looking for I? Cover up I, I'm left with F divided by B times by L. And finally, if they want to know the length of the conductor, cover up L, and you're left with F divided by B times by I. Have a close look at that, eh? And finally, the last one. I'm trying to find ways of recording these quicker. I'm not sure if this is the way to do that. Statement 14. Now this is triple higher only. Explain how the force on a conductor in a magnetic field is used to cause rotation in electric motors. Right, without going into the ins and outs too much, if we have a magnet, north and south, drawing your magnetic field lines, going from north to south. And what we'll do this time is we'll have a coil of wire that goes in, comes round the back, and comes forwards. Now what we've got here is a split ring commutator on there and on there. Then we've got some brushes. It's a brush there and a brush there. Positive end of the battery, negative end of the battery. We're talking about conventional current here, which goes from positive to negative. Now you can see that the current will come round this way, and that first the current will come in this side, come round there, and it'll come out this way, and then it'll come out that way there. So if we used Fleming's left-hand motor rule, which I've talked about previously, if you use your second finger and point that into the screen, and then if you put your first finger, which shows the field going from left to right, what you'll notice is that this side of the coil is going to get kicked downwards. The movement will be down. Now this is good though, watch this. As the current goes through there and comes through the back, the current comes out of the screen now when it's coming down the left hand side of this spinning blue coil. So keep your first finger pointing from left to right. No, knuckles is the north, fingertips is the south. So keep that first finger pointing to the right. But your second finger now rotate it so that it comes out of the screen towards you. And as it does that, your thumb will flip upwards. So remember, your thumb shows you the movement of the wire. So this side of the coil is going to spin up, that side of the coil is going to move down, and because we've got this split ring commutator, that means that the current is always flowing in through this way and out through that way, and we get a constant spin. So that's your DC motor. And that force on the conductor, because it's in the magnetic field, can be used to cause rotation in the electric motor. So we've created an electric motor here. That's what we've basically done. An electric motor is a coil of wire surrounded by a magnet. It gets a little bit more complicated than that, but that's for GCSE Physics. That's pretty much it. And that's the whole lot done. It's the whole unit. So there's quite a lot there that we've gone through. I hope it's been useful for you. I do like this 3D software. It'll make some great mind maps, I'm sure of it. But until I get used to it, it takes quite a long time to do the video there. So comment below, let us know what you think. Tell us how you think I can use this software in the future, or if you might have liked it. Okay, so apart from that, good luck with your exams. Work hard, be nice, and I'll see you in the next video. Bye for now.